That's concentration versus time. You're going to see this up here, concentration versus time. Here are your concentrations. Okay, here is the time value. And you're going to have to put them into your graphing calculator correctly. And you're going to look for the 3 different trends. You're going to do concentration versus time. You're going to do the natural log of concentration versus time. Then you're going to do the inverse of the concentration versus time. After you get all that data put in there, you're going to either graph them or use the linear regression line. You can use that too to figure out which one the order is going to be, because it's either going to be 0, first, or second order based off of those trends. 0 order if the straight line comes out to being concentration versus time. First order if the straight line comes out to being natural log versus time of the concentration. And then it'll be second order if it's the inverse of the concentration versus time. So let's go ahead and get our calculator set up so that we can make sure that we're entering them correctly. Okay, so the first thing you want to click is the, hey, voice off, listen up. First thing that you want to do is make sure your diagnostics are on, so you need to click mode, which is right next to the second button here. Mode, make sure you go down, make sure you check that your stat diagnostics are on. You need that on. If it's not on already, make sure it's on now. So that was the second mode, right next to where the quit is. Click on mode and then scroll down and make sure your stat diagnostics are on. Okay, once that's done, then you need to click stat, which is up there towards the top under the delete button. Click stat, and you want to do 1 for edit. Now, you're going to type the time in list 1. Type the time down in list 1. You're going to then, in list 2, type in the concentrations. I will show you a quick, easy way to do list 3 and list 4. But for the moment, go ahead and type in list 1 is your time. List 2 will be the concentrations. So go ahead and do that. Now for list 3, the easiest way to do this is go up to the top and highlight at the top where it says L3 and hit enter. You hit enter, then it brings up the L3 equals at the bottom. All you have to do now is type in the LN for natural logs and put in list 2, because list 2 is the concentration, and then it will do all of the natural logs for you. You don't have to do any typing. Right? Okay, now for list 4. Same idea here. Go up to the top and highlight list 4 at the top, hit enter. And then the L4 equals at the bottom pops up, and do 1 divided by list 2. And then you hit enter, and it will put in the inverse concentrations for you. Okay? Now you have 2 choices. You can plot them using second stat plot, which is the Y equals button at the top left. Okay, but you need to make sure that you have each one L1, the time versus the first plot would be L2, the concentration. The second plot would be L1 versus L3. And then the third plot would be L1 versus L4. And you want to make sure that you have only one on at a time to plot the graphs. So we would turn on plot 1, and then I'll turn off plot 2 on mine in particular. But make sure your X list is always list 1, and your Y list is always the concentration one you're trying to find. So L2 is just regular concentration. L3 is the natural log of the concentration. L4 is your inverse concentration. So when we graph this, it's not going to pop up very nice. You're going to have to use the zoom button in the center at the top by your graph up there. You're going to need to do zoom, and then number 9, which is the zoom stat. Now, as you can see here, for our concentration versus time, it is a curve. So this is not the order of the reaction, because it didn't come out to be a straight line. Now I'm going to go back up and plot the second one. Second stat plot, the y equals button. I'm going to turn off plot 1 and turn on plot 2. And you will see here when I graph this one, this is going to be the time versus the natural log of the concentration. I also need to zoom in, the middle button up by the graph, do 9 for zoom stat. And you see now this one does appear to be a straight line. So the natural log of the concentration versus time, this one happens to be the order of the reaction, which is first order. We can always go and verify our list, our third one there, just to make sure if you care. We would need to turn off plot 2 though. If we graph that one, you will see here, once it's done graphing, taking a moment, you will also zoom in, but this one should also come out to being curvy rather than a straight line. And look, it is. It's curving upwards. It's not a straight line. Now, if you don't want to bother with the stat plots and you don't want to do the graphs, you can always run a linear regression. Okay? So if you'd like to use your linear regression, you still go under stat, and then you need to go to scroll over one to calculate the CALC. And you need to do the linear regression AX plus B, which is 4. You need to type in your lists here. This is list 1 versus list 3. Okay? So this one would be the time versus the natural log of the concentration. And you go down to calculate, scroll down to calculate at the bottom, you click it, and you can see here my R values are 0.99999, which means it's about 1, which would mean it would be the straight line one. Okay? However, if you were going to look at a different list, so run the linear, go back up to the linear regression, go into the calc, and now I'm going to change the list to list 2 instead of list 3, which was the one. If I run the linear regression on this one, you will see it doesn't come out to being like almost perfectly 1. It should come out to being almost perfectly 1. This one, the R's are 0.88 and 0.94. That would mean it is not forming a very good straight line. So you can graph it and look at the visual aid. I like to graph it. Or you can run the linear regression if that is more comfortable for you and quicker. Yes? To do the linear regression? I went to stat, over to calc, 4, and then you just scroll down, and you can change it. So I'll do L4 here. You can't do that in yours? Okay, well, I will have to see about those older calculators. But as you see, if we run L1 against L4, which is the inverse concentration, this also does not produce a straight line based off of the linear regression. Okay? Both of them should be right at 0.999, almost 1, if that is the straight line one. That's fine, because it could be the negative slope one. It just has to be a straight line. Remember that concentration versus time and natural log of concentration versus time, even if they're straight lines, the slopes can be negative. Okay? Okay, so after all that wonderful calculator stuff you just did, you figured out the order of the reaction happens to be in first order. Okay? Now, we do have to calculate the K, or the rate law constant here. So, how would you figure in order to find K after you figured out its first order? What could we do? Any ideas? We use our first order equation. That's a great idea. Then what can we do? Solve for K using what? The first order equation, but what data in the first order equation?
You have to pick one concentration.
Yeah.
Okay, so first order equation, pick a line, any line. And actually you can pick a different one than I'm going to do just to check and make sure we're all going to get the same K value. So I'm going to choose this one to use in my equation. Remember, it's first order, so we're using the natural log equation. Correct, and we're solving for K here. So we get, for this particular one, I'm going to do and the time here would be 300. So you pick a different line than I did and see if we're all going to get the same K value when you calculate. So what do we get for K? K equals 6.9 times 10 to the, or 3 times 10 to the negative 3. And what is the units on this K value going to be since it's first order? Time is in seconds, and units of K? Just seconds to the negative 1, yes, there, per second. Exactly right.
Why do we modify the concentration? Properties?
Yes, because this you can change into this following natural log properties. So when you subtract right here, it turns into
But if
that.
we did the original
It still gives you the same answer, correct. If you do them separately, you would still get the same answer. Okay, but yes, that follows log properties, being able to do that. Okay? Okay, before we get there, let's take a look. This is a very nice chart in your notes to summarize everything you need to know about integrated rate loss. And it even gives you the differential rate law here first, showing what that looks like. Comparison to the integrated one where you have the equations. Okay? Remember that you do get the first order and the second order on the formula sheets. They are on the formula sheets. Also on the formula sheet is the half-life of the first order only. So keep that in mind as well. It also tells you and summarizes for you who gives you the straight line, what order that would be, the relationship of the rate constant to the slope of the line. Remember, 0 and first order always have the negative K because it's a negative slope. And last but not least, the half-life equations down here. So this is a really good place to have, doing your free responses and your multiple choice questions, have this out to be able to look at it, and it will summarize everything for you. All right, last but not least, the Arrhenius equation. And yes, this is a division sign here. By the way, that means divided by. The activation energy, negative activation energy divided by RT. And a new variable in here is the frequency factor. Remember, this little section here really is like, this part is e to the x, and the x in this case is the negative activation energy divided by RT. Okay? Yes? It means divided by, like the activation energy is being divided by the RT. It's division in that exponent. It's very confusing. That's why I'm specifying there. Some people thought it looked like an I yesterday. This is actually the activation energy divided by RT. R being the gas law constant, yes, but it is the 8.3145 gas law constant, this guy. And that one is also, this one is on your formula sheet, so you don't have to memorize it. So this is on the formula sheet. All right, temperature has to be in Kelvin. And basically what he discovered is you can put temperature in with this, the rate constant, and then this new frequency factor idea, which really is everything that may cause them to orient themselves better or collide better, okay, that are favorable there. So things that could influence the frequency factors would be like catalysts. Obviously, in this case, temperature is kind of held separately in the equation, but particle size, things like that, that would make them collide faster and better to make them react. Now, this version of the equation is a little weird to work with, so we do put it in linear form to make it easier to look at and adjust to. So the linear form is shown on your chart down below here. This one being the linear form right here. Okay. Where you have the natural log of the rate constant equals the negative activation energy divided by RT plus the natural log of A. So a graph of the natural log of the rate constant versus the inverse of temperature will be aligned with the slope. And the slope is really cool because the slope gives you the negative activation energy divided by the R constant. Therefore, if you graph it, you can figure out the activation energy amount. Actually give it a numerical amount. Down here too, with manipulation, you can manipulate it so that if you were given two temperatures and a K, you can find the other K. If you were given the two temperatures and the two Ks, you run different experiments at different temperatures, you can figure out the activation energy. So, and conceptually, you just really need to focus on the fact that this arrangement, the natural log of K versus the inverse of temperature, gives you the ability to calculate and find the activation energy amount. Okay? So while you're looking at that, that's what you need to concern yourself with. And last but not least, to sum that up for you, remembering what we're talking about here in terms of activation energy. Oh, here's another graph for you, just showing you the same thing where you have natural log of K versus the inverse of temperature. And you can find the slope. Once you get the slope, you know the R value already, you can find the activation energy. But summing everything up once again, if it's run at different temperatures, the activation energy of the reaction can be determined. And remembering where it is on the potential energy diagram. Make sure you know what the potential energy diagram is. This is the potential energy diagram, where it has the reactants, the products, the activated complex, okay? Reactants, products, the transition state up here with the activated complex, your intermediates starting to form, and so forth. Because you will most likely be asked to draw potential energy diagrams, as you saw in the thermo section. They can also put them here in kinetics as well. So you can see these pop up in different types of free responses. So don't forget that that thing is called the potential energy diagram. Okay? We good? Yes. Any questions? All righty then.